Hello architects and developers, and welcome to another video on building serverless applications with Rust. It has been a little while. It's been a few weeks. I've been moving house, I'm somewhere new, I've got my plants, all this other stuff going on. But now we're back, we're ready to talk about more serverless Rust goodness. And what I want to do with a few videos going forward now is to kind of combine the two different series of videos that I've been producing recently. Because you might have been watching some of my recent videos about event-driven architecture, about some of the patterns that you will see in event-driven architecture, particularly one I received recently that got an awful lot of interest, looking at the differences between streams, queues, and buses. And what I want to do for you today is I want to make that more practical, because you might have watched that video and thought, well, this is great, James, but actually, I need to kind of imagine what this actually looks like when I use this in the real world. So what I want to do over the next few weeks is using Rust, using serverless, using Lambda, to demonstrate how you can actually build a high-performance queue processor. That's what we're going to cover today. But then in the next few videos, we're going to cover an event bus, an event processor, and also a stream processor, so that you can use these things combined with Rust to build incredibly high-performance, sustainable, and safe message processors for your applications. Let's get straight into it. And I actually want to start with a release that me and the wonderful Benjamin Pyle have released recently. This is a website, serverless-rust.com, and it covers a whole range of different ways you can build serverless applications with Rust, including things like message processors, database processors, APIs, building with containers and Rust, everything you need to build serverless applications with Rust. And in this website, you will see content on streams, on queues, and buses. And we're going to start with queues today. And we're going to use this actual example as something we're going to talk through today. So if you go and have a look at this website, you will see there's information about SQS, about how SQS and Lambda work together, the way to structure a project in the right way when you're building with Lambda, Rust, and serverless, and of course, the actual Lambda code itself. But if I'm not just going to show you this on a website, I want to show you this in some actual IDE. So let's jump over to Rust Rover now and actually have a look at how you can process SQS messages with Rust and Lambda. And the way this project is structured, it's split up into the actual Lambda function code that's in charge with dealing with the Lambda runtime, pulling the messages from the queue, processing the messages. And then there's actually this shared folder, and it's the shared folder that contains the actual business logic, the things that are actually relevant to your domain and your specific use case. And the reason for that separation is one of portability. This is an example of the ports and adapters, or clean architecture, or hexagonal architecture style, whichever word you want to use to call it. And that allows you to switch and change your actual piece that's dealing with the queues, the actual Lambda code, from the actual business logic itself. It keeps your business logic portable. So to start with the actual message processor, we'll look at this main.rs file. This is the actual entry point. When you actually compile your Rust application, the entry point for that executable is going to be this main function. And in this main function, you're setting up a tracing subscriber. You're setting up some kind of logging. We're not including the time in this logging because that gets included by the Lambda runtime itself, by CloudWatch. And then I'm actually executing the Lambda runtime. So this code here actually comes from the Lambda runtime. If I go over to my cargo.toml file, you see that I've actually got the Lambda runtime as a dependency in this project. And this run function is actually what's going to pull the Lambda runtime API. And then I'm telling that function to actually call this service function, so I can actually then pass in a closure that's going to be called every time a new invoke comes into Lambda. So run's actually what's going to pull the runtime API, and then anything inside this service function is what's actually going to be executed for each individual request. And if you're familiar with Lambda, this is the kind of initialization phase of your Lambda function. This is where you would set up things like database connections, shared SDK clients, all the things like that. And then it's the actual handler here that's actually going to be the function that's called for each individual invoke. If I scroll back up in this file now, you can actually see that function handler function. This is what's actually going to be called for every single request that hits Lambda. You'll notice I'm taking a single parameter into this function, and that parameter is an SQS event. And this Lambda event, SQS event structures, they come from a shared dependency, specifically this AWS Lambda events crate. And that actually includes structures for the majority of the actual event payloads that you could invoke a Lambda function with. And in this case, we're using this SQS event. And you'll notice I'm returning a result, as you would. And actually, the first property of this result is an SQS batch response. And what this allows you to do with SQS is to actually have partial successes and partial failures. So you can, let's imagine your Rust Lambda function receives 10 messages from an SQS queue. 9 of them complete successfully, and 1 of them fails for whatever reason. Maybe it's a poison message, maybe there's something wrong with it, maybe it's a different format. Who knows what the possible reasons for failure could be, but there will be a failure eventually. This allows you to tell SQS that 9 of the messages were successful, 1 of them failed. Please push that message back onto the queue for reprocessing. And you'll notice what I do as I'm starting out here is I create a new vector to hold my batch item failures. And then as the message is actually processed down here, and I'll get into what that's doing in just a second, if the message processing is an error, I'm going to push a new item into that vector, and I'm actually going to include the message ID of the message that failed. When I come to then return the response, Lambda and SQS and that integration know which messages were successful and which messages failed. So anyway, back to this event payload. The event payload that comes into Lambda is going to contain a vector of the individual messages. So the way the Lambda and SQS invoke works is what's called a poll-based invoke. So the Lambda service is going to poll the SQS APIs on your behalf. It's going to pull out a batch of messages, and then it's going to pass that batch of messages into your Lambda function as an invoke. So you will always receive, when you're using SQS and Lambda, a vector of all the messages, as opposed to just a single message like you would with something like API Gateway. So the first thing we need to do logically is iterate over that set of messages. I'm doing a simple for loop over each of the records in this payload. And then the first thing I'm doing is getting the message ID. This is what is then used if there's a partial failure to be able to say this one failed, this one succeeded, so on and so forth. Then this line of code here is where I'm actually parsing that SQS message as something that's relevant to my business logic. And I'm doing that using a feature of Rust called the from trait. And it's a feature I really find valuable in situations like this. So this try into function, this is going to try and convert the structure that comes in to a different structure. So I've declared this new message variable as a type result of a new message. And this new message is something that is actually relevant to my business logic. This is the actual message that my domain is processing. And then if that parse fails, I get a message parse error. If you go and look at the shared application code now, you will see right down at the bottom here, I've implemented this try from trait. And I've implemented that for my new message struct. This is something that is specific to my business logic. And what this allows me to do is actually centralize the code that's in charge of parsing that SQS message and parsing it into something that's relevant to my business logic. So you'll see inside this function code here, I'm checking to see if the body actually exists, if the SQS message actually has a body. If it doesn't, well, then I'm going to return a empty message body error. And if it does, I'm going to try and use JSON serialization to deserialize the body of the SQS message into an actual struct, this new message in this case, and then I can return that new message. And this allows you to write this really clean code as part of your message process to say, actually, I want to take my message that comes into SQS, and I want to try to convert that into a new message object. I think this reads really well. It's quite legible. It centralizes the logic. You've got single purposes for things. Now, one thing you have to be aware of if you're doing this, if you're using this from trait, is you can only actually implement the from trait for structures that are inside your crate. So I couldn't implement the from trait directly to the SQS message object that comes in from SQS. So you see I'm creating a new instance of this internal SQS message structure here. And if you go and have a look at that internal SQS message, this is just a wrapper around the actual SQS message. And this is what then allows you to implement that from trait for the SQS message. You just need to create this simple wrapper type around it. So it's not too complicated, but you just need to create that little wrapper to actually be able to implement that from trait and write some really nice clean code. And then all I'm doing down here is just handling that message. So I've got this new message handler. Again, this is something that comes from my actual business logic, my shared code, my domain code. In this case, the actual log message for this handler is actually just going to write a message to my logs, which is kind of trivial, but it gives you the idea of how you can implement this. Now, the beauty of building things in this way, of separating the code out in this way, is that actually if you then need to implement a different use case, a different SQS message processor, you can keep the Lambda function code almost identical. It's going to be almost exactly the same. all you will need to do is come in and change that new message and that new message handler to be types and business logic that are specific to your application. And when it comes to templating and starting to work with Rust and Serverless and Lambda, this is now something that you don't need to worry about. You can create this template once. You can go and clone the repo that me and Ben have created, take that code, implement your own business logic, and you will be off and running, building with SQS and Lambda. So you come in, you change this new message structure to be exactly what you need it to be for your business use case. You re-implement this handler to handle the message you've created, write all your business logic here, and in the main, this code here isn't going to need to change. You just need to obviously update the type names from new message handler and new message to be something that's relevant to your business logic. This will handle batch failures, it will handle all that stuff, and you can just get started building high-performance queue processors. Let's actually go off and deploy that now. So if I flick over to my terminal window, I've already navigated into this directory, and I can run a simple SAM build command. This is using AWS SAM. You could equally be using the CDK to do things like this. This is a beta feature, so compiling Rust applications is a beta feature of the SAM CLI. So I just need to hit yes there, and SAM is now going to go off and compile my application, which happened really quickly because I've not actually made any changes to my code since that last compiled. I can then, of course, run a SAM deploy command, pass in my custom profiles. I'm deploying to a different AWS account for this demo, and this will now go off and deploy. Again, this should complete really quickly because I've not actually made any changes since last time I deployed this. And while that's just deploying, I'm just going to flick back over to the serverless Rust site. If you scroll right down to the bottom of this documentation site, it will even give you instructions on how to actually test out what you've just deployed. So you see I've got the two commands at the bottom here. I'm going to manually send a message into my SQS queue, and then I can run the SAM logs command to actually pull down the logs for that instance of my Lambda function. That is now finished deploying. I can now run the AWS SQS send message, hit that send message command, and this will then send a message onto my queue. So there's a message in the queue now. And if I just cancel out of there, come back into here, and I run SAM logs, again, passing in my profile, I will get the up-to-date version of my logs from SQS, which is fantastic. And if you actually look at the numbers here, just to actually double down on the performance of SQS and Lambda and Rust, and if I just slide myself up to the top there, you see actually these numbers here. So this is a new message that has come in. The message is hello. And if you look back at the actual message I sent to SQS, the contents of my SQS message were just the word hello. And that actually completed in 14 milliseconds as far as the initialization phase, and then it actually took 1 millisecond to process. Of course, this is only writing a log message right now, but if you imagine this was a call to something like DynamoDB, that's still going to be single double-digit millisecond response time, depending on exactly what you're doing in DynamoDB. And it did all of that, so a total 16 milliseconds of build duration with just 128 megabytes of memory. Performance, speed, sustainability, and safety all in one lovely little Rusty package. And that is really all there is to building with SQS and Lambda and Rust. And you can actually take that template. I'll pop a link in the description below. You can go to the documentation site, you can go to the GitHub repo, you can clone it, and you can start building from that exact template. Switch out that shared code, put in your own business logic, and get started building high performance queue processors for your Rust applications. I'll see you in the next video to talk about stream processing, something that can be really, really powerful using Rust, especially if you're doing things with IoT devices, sending things from IoT devices into a central stream and then processing the work off that stream, because Rust can do parallel performance computing really, really well. I'll see you all there.